Hi, I'm Dhairya, roll number 2024185, presenting project group number 17, the Handloom Artisan Market Management System. See this, India's handloom sector is deeply unorganized. Artisans in small villages have no direct market access and multiple intermediaries which leaves them underpaid or completely unpaid. Our system solves this by building a centralized database management system that would connect artisans directly to buyers, removing the intermediaries that affect them. The target users are mainly three groups. Our first one are artisans who register their products, buyers who place orders, and administrators or policymakers who need analytics on regional performances. The key features are artisans registration with certification, tracking, also product listing with livestock management, direct order placements with agreed pricing, payment tracking, and artisan income analytics. A database is essential here because we have multiple related entities, artisans, products, certificates, orders, buyers with complex relationships, integrity constraints, and concurrent access requirements that a spreadsheet simply cannot handle. Our concept model has five entity sets: artisan, handloom products, buyers, orders, and certifications. The producers relationship is one to many. One artisan produces many products, but every product must belong to exactly one artisan. Handloom product has total participation because a product cannot exist without an artisan. Place order is also one to many. One buyer can place many orders, and every order must reference to a buyer. Contains links handloom product to order in another one to many relationship. One product can appear in many orders, and each order can contain exactly one product. Certified by is also one to many from artisan to certification. This is because an artisan can hold multiple certifications belonging for exactly one artisan. Converting to the relational schema is very straightforward. Each entity become a table. Foreign keys implementing the relationships. For example, handloom product has artisan ID as a foreign key, referencing the artisans. The constraints we enforced: price must be greater than 0, quantity available must be at least 0, and payment status is restricted to paid or pending. And phone numbers are unique across both artisan and buyer. The database has 7 tables: artisan, handloom product, buyer, order table, certification, order audit log, and artisan income. The last to support our triggers and are covered in task 5. Every table has a primary key with auto increment. Foreign keys enforce referential integrity. For example, you cannot insert a product without a valid artisan ID, and you cannot insert an order without a valid buyer ID and a product ID. We created 7 explicit indexes to speed up the most frequent query patterns. IDX product artisan on handloom product speeds up the join between artisans and their products. IDX order status on order table speeds up the very common filter for pending orders. IDX order buyer and IDX order product speed up the order joins used in almost every analytical query. For the simulated data, we populated 5 artisans from different regions: Odisha, Gujarat, Uttar Pradesh, and Kerala, each with a distinct craft type. We have 6 products covering silk and cotton with different techniques, 5 buyers ranging from individual customers to government institutions, and 6 orders with a mix of paid and pending statuses. The data was designed to be internally consistent. Stock quantities reflect actual order placed, and the paid orders have corresponding audit log and income records. We implemented 15 SQL queries of increasing complexity. Let me walk through these key categories. The simplest query uses the basic filters. From query 5, particularly query 5, it finds all the orders where the payment status is pending, a single where clause on one table. Query 9 finds low stock products using a threshold on quantity available. The join queries are more interesting. Query 12 is a 4-table join. It connects order table to buyer, handloom product, and artisan to produce a complete order view showing the buyer name, product, artisan, and quantity in one result set. Query 7 uses a left join with a null check to find artisans who have received 0 orders. Without left join, artisans with no matching orders would simply disappear from the result. The where order ID is null pattern specifically catches those missing matches. For aggregation, query 6 computes total revenue per artisan by joining 3 tables and using sum with group by. Query 14 ranks regions by artisan count using count and order by desk. The most complex query was query 15, which uses a scalar subquery in the where clause. It selects the artisans whose products are priced above the overall range. The subquery select average price runs once, and its result is compared against each product's price in the outer query. Query 2 uses not in with a subquery to find artisans with no certifications, a set membership test rather than a join. These 15 queries together cover filtering, joins, left joins, aggregation, grouping, ordering. The application is a Python Flask reset API that uses SQLite standards library. No, and it does not involve ORM. Every database interaction is an embedded SQL statement using parameterized queries to prevent injection. The front end is a single HTML file that communicates with the Flask server over a REST API at port 5050. When you open the UI and place an order, the browser calls post API orders, the server runs the insert, and the trigger fires automatically inside the same transaction. Trigger 1, TRG reduce stock on order, fires after every insert on order table. It first checks whether the quantity available is greater than or equal to the ordered quantity. If not, it calls raise abort, which cancels that entire insert and returns an error to the application. If the stock is sufficient, it runs an update to detect the ordered quantity. This logic lives entirely in the database. No application code can bypass it. Trigger 2, TRG log payment and income, fires after an trigger 2 TRG log payment and income fires after an update of payment status on order table, but only when the status changes from pending to paid. The when clause ensures that it does not fire for any other updates. It then performs two inserts, one into the order audit log, which creates an immutable payment record, and the other one into Artisan income, crediting the artisan with agreed prices multiplied by quantity. Both inserts happen automatically with the original update. Let me demonstrate. I will place an order in the UI and you can see trigger 1, fire, and the stock reduce in real time. Then I will mark an order as paid and you will see the audit log and income record appear. Moving on to task 6, demonstrating the 6 transactions covering all 4 asset properties. T1 is a normal commit. Placing an order wraps the insert and triggers 1s stock deduction in a single transaction. Both succeed together. This demonstrates atomicity. The order and the stock change either both happen together or neither of them happens. T2 is another normal commit. Marking an order as paid triggers trigger 2, which writes the audit log entry and artisan income record. All 3 writes the update and both insert. They insert the commit automatically. This demonstrates consistency. The database moves from one valid state to another. T3 demonstrates a deliberate rollback. We attempt to order 999 units of the double ikat sari, which only has 2 in stock. This will raise trigger 1 and hence it will abort, which automatically rollbacks into the insert. The stock remains at 2 and no order record is created. T4 uses save points, a nested transaction feature. Inside one transaction, we insert a valid order, set a save point, then attempt an invalid insert with a non-existing buyer ID. The foreign key constraint fails, we roll back to the save point and commit. The good order is saved while the bad insert is completely undone. T5 is a conflicting transaction scenario. 2 threads simultaneously try to update the same stock value. By using begin immediate, each thread must acquire an exclusive write lock before proceeding. This forces serial execution. Thread B commits first and then thread A waits, then commits. The final stock equals the initial value minus both the deductions. No lost updates. While T6 demonstrates foreign key enforcement, attempting to delete buyer 2 Fab India, who has active orders with Pragma foreign keys on, the delete is rejected with a constraint failure and rolled back. Referential integrity is preserved. In summary, our project demonstrates a complete database application lifecycle, from requirements to schema design, query implementation, a trigger back application, and ACID asset complaint transaction management. Thank you so much.